Thank you, Richard. So the reason is when I prepared the slides, I realized the title is too long. So as I decided to cut secure and crime. So there's no crime on cyber. Okay. So we talk about hardware and the role it plays in cybersecurity. And when you talk about the security, talk about the trust, you think about your valuable things. In the past, it was jewelry, money, or whatever things. And now people talk about their identity, their privacy. And whenever you think about these things, you think the safe place will be a safe. So this is the mechanism people use for many, many years to keep your secret, to keep your valuable things. And what is hardware here? So hardware is the safe itself, the building block. So that is what we're seeing. I mean, the sense hardware is the enabler for all this trust and the security. You can have this mathematical, proof about a crypto stuff. You can have software implementation, but at the end, it has to have run on hardware. You have to have these logical gates, transistors working for you to do all the computation. And not very long, people realized that hardware can do things much better. So that is why they started doing dedicated hardware to do security and trust. So that is why you see a lot of these little things, and then they have chips embedded, and then they do something related to hardware. And something more interesting is something people call the secure coprocessor, or accelerators, which is dedicated to hardware security, doing security protocols and calculations. And eventually this is something called, people decide to give a name called the TPM, the Trusted Platform Module. And finally, I have the last E word here, says enforcer. And this becomes enabled on many, many devices, which basically before you access the CPU, the system, they check your biometric information. They check your other information. If you don't pass this level, you don't get into the system. And that outside, it is like a firewall, like a gate, and this is controlled by hardware. So that is why I'm saying hardware now becomes more and more active in security. Now it's become the enforcer. It protects the system, so if you don't pass this, you cannot get into the system. So now we come back to this safe here. Once you have a safe, normally you have, used to have a lock, have a key, a physical key. And then later on it becomes more advanced, people decide to put something called a key combination. Okay, so most of the safe, they have a key combination. And what you do is, so once you have the key combination, so you have to be careful where you store this key. Okay, so think about for our keys, well, when we do this secure computation, you say, okay, I store my key in secure memory. You put it into memory, you think it is safe, because you are not doing hardware design. So when you do hardware design, you say, okay, so it is secure memory is not secure. So there are a lot of things, or a lot of ways you can break the memory. You can get the key out. So the most popular way is called the reverse engineering. So people peel out your chips layer by layer, and then trying to figure out what is the key bit by bit. And then if they don't want to peel it out, they can do some other things which called the side channel analysis, or side channel attack. And this I'm going to have a separate slides talking about this. And also they can do micro probing, trying to see what is inside. They can do fault injection, trying to inject faulty input, and then see how your system behaves. And then from that, trying to, in some sense, guess what is your key. And also if you think about software, that is something built on top of hardware. And people can use software to write malicious software to get your key out, get your secret out. So if you think about all these things, so the key where you store in the memory is not safe enough, because the software has interface with main memory. You can give a wrong memory address, trying to go where the key is, and then fetch it, get it out. So that means if you have a very, very nice design of a crypto protocol, which means you have a very nice built safe. But however, you put the key combination on top of this safe, put it on a sticker, write on this, whatever this 3748, the key combination. So that is exactly the same thing if you do here, and then if you don't protect your memory. And then people will just come to here, oh, it's a nice safe, but I know the key combination, so I'm just going to open it. So it's not going to protect your secret at all. So now let's see what happens if I say, okay, so I'm not going to put my key stick on the safe. And then if you watch those old movies, the thieves, they are really good. I mean, the things they can put their ear on the safe, and then they can rotate this key as this lock, and then trying to, from that tiny voice, they can tell whether it is correct or not. So that is something similar, which we call, side channel attack. So for this side channel analysis attack, what the attacker do is, they let your system run, and then they try to monitor some side channel information. And then from this side channel information, they try to perform data analysis. And from this data analysis, they try to reasoning and then trying to guess or trying to learn what is your key information. So what are the side channels? So the channels can have a lot of things. So I mentioned earlier about the cache memory. You use your key to do encryption, your decryption, and the key will be staying in cache for some time. So people can get from the cache. And whenever you do computation, you use power. There's current flowing around in the circuits. And then there's timing based on the computation. Okay, finishes computation faster or lower or slower. And all this information, the attackers, they can collect and then try to reason your key. And also I put something about scan chain. This is for hardware design. And also this electromagnetic radiation, and people can also use this to get your key. And which is useful, interesting about this is for people to collect your EM signals, they don't have to have a physical access to a system. As long as they are within meters of your system, or maybe within 10 meters, 20 meters, then they can get that. Okay. And what is really surprising is sometimes even the output signals itself can carry some information. So this happens in the case, for example, attackers give you a faulty input, or then they can analyze the output. From that output, they can get something. Okay, so now I'll give you one small example. So this is one of the 2 or 3 small examples. So hopefully, you can learn something, after this 1 hour. So this is a mathematical operation called modular exponentiation. And it is very simple here. So what it does is it's going to raise a number, which is 2 in this case, to the power 4, which is, we know it is 16. And I'm not asking for 16. I'm asking you to do this at a modular arithmetics, which means 16 will be mod by 10. So it's going to be 16 divided by 10, and then take the remainder. So in this case, you say, okay, it's easy. 2 to the power 4 mod 10 is 6. Okay? So that is the basic definition. And why we are concerned about this? Because this is probably the most popular math formula people use for crypto, particularly for modern crypto. So I'm going to give you only 2 examples here. So the first one is called the Diffie-Hellman key exchange. So this talks about 2 entities, Alice and Bob, how they can change their keys. And the key idea about this is they're going to change some information, and then eventually both of them, they are going to evaluate a to the power x to the x, and then raised to the power x sub a. Okay? And on the other end, the other person is going to calculate a to the power x sub a, and then raised to the power x sub b. And then mathematically, these 2 are the same. But then the thing, that is how they share the secret. People sit in the middle, then they cannot observe this calculation. So eventually they get the same key, which they can share to do any secure communication. And the second one is even more popular. This is the RSA public key encryption. So when people do the encryption, decryption, so they have the plain text raised to the power e mod n, and that is the ciphertext. When you do decryption, you have the ciphertext, you raise it to the power d mod n again, and then you get the plain text. This c and the e and the d, they have some mathematical relationship. Okay, so but the bottom line here is the operation you are working on is this modular exponentiation. And you will say, okay, so what is new here? So I just raise this to the power whatever and then do the mod. But now if you think about for RSA, we're talking about 512-bit key. And now people talk about 1024-bit keys. So that means even for much smaller size, we're talking about trying to calculate things like this. So a 1024-bit number raised to the power, which is 1024 bits, and then mod, another huge number. So how can you do this? You cannot say, even for this case, I'm going to raise this number to 10 million times, or do 10 million multiplications, and then do the module. So nobody can afford to do that. So engineers, people are very smart. So when you ask them to implement something, they say, okay, so what you need is you want to calculate this and then do the mod. You don't really need this intermediate result, which is 16. So I don't have to calculate this. As long as I give you this 6, I'm fine. So then they decide to do this. So for example, I'm going to raise a to the power 16. Instead of doing that, I'm going to do this way. If you do this, you see, okay, what I'm doing is I do 4 squares. And then you see you are lucky. So how about if I have something which is not a power of 2? So this is, I can do something this way. So a to the power 23 becomes a to the power 16 times a to the power 4 times a squared times a. So if add up the exponents, it gives you 23. And then if you see this, the number of multiplications or squares I'm doing is much, much fewer than 23. And then if you think about the 1024-bit key, so ideally you're probably only going to do 1000 multiplications or squares. Becomes much, much faster. And this is a very well-known algorithm. It's called a square and multiply. And that is, in real life, how most of this modular exponentiation is implemented. And this is a pseudocode how to do that. And the key thing here is I'm going to convert this exponent into binary. And then based on the binary, whether it is 1 or 0, I'm going to do a square here. And then if the bit is 1, I'm going to do a multiplication. So that is why I call the square and multiply. We say this is good. It just, speed up your calculation. I don't know how many magnitude of becomes much faster. But then you see one thing here is interesting here is this operation. You do it if and only if when the ith bit of the key is 1. If the key bit is 0, you're not going to do this operation. Okay, so whether you do it or not depends on the value of the key bit. And that is your secret. And remember, when we do these multiplications, they are huge numbers. So it's not going to get calculated without any effort. You have to spend power, you have to spend time to do this calculation. So that is, people say, okay, they can observe from set channel trying to see, oh, it takes a little bit longer for you to do this iteration on one of these things, and then they can guess at this iteration, the key probably is 1. If the next round, the calculation takes a shorter time, the next key bit may be 0. So that is eventually people discovered that probably 20 years ago in the late 90s. And it turns out this is something really, really powerful. So this is something I copied from the EE Times. And it shows you the power trace. So on the y-axis, you can think about it is the power consumption or the current. On the x-axis, think about this as the time. So every single cycle, clock cycle. So this green ones means short. This you can see from whether it is high or low. And the shorter ones, it is normally for square. Because people do square, it is a special, so they have smart algorithms to implement square. And then if you do a general multiplication, normally it takes a little bit more power. So what you see from here is you see a couple of higher ones. These are the things where I do multiplication. And then from the algorithm, you realize that whenever I do multiplication, the first thing I do is I always do a square. So that is, whenever I find a multiplication, I try to combine this with the previous square. So that is why I have this red here, red here, red here. It looks like 2 cycles for me to do square and multiplication. And for other green ones, they are only square only. Now if you go back to the algorithm, this tells you that for these green ones, they correspond to bit 0. The red ones corresponds to bit 1. So that turns out to be the power analysis attack. And then in the past 20 years, people have invented a lot of smart ways trying to prevent this attack. And then the attackers also come up with some other things trying to keep on attacking. Okay, so another thing, let's try to go down a little bit to the circuits. Yes?
How about when you artificially slow it down when you don't have to do multiplication?
That is one of the earliest. Countermeasures. So they are always trying to make your power trace to be even, constant. But then there's something called a differential power analysis. Even if it is constant, they can still try to get out of your key. So, and they are talking about using redundant hardware, trying to do 2 computations at the same time, so they can compromise with each other. And then they talk about throwing some random calculation. This, in addition to adding overhead, again, it is not to be very, very effective to prevent power analysis. Okay, so that is normally if you go study, security, it is always about two sides, good guys and bad guys. So bad guys start attacking your system, you try to make your system secure, and then bad guys come back again, so they're always moving up. Okay, so this is you can think this as a very simple control system. So I have three states, 0, 0, 0, 1, 1, 0. And this address tells me that the control command. So if I receive a bit 0 or input 0, I move to states from 0, 0 to 0, 1. So this shows you, how this control system works. And then if you learn the basic digital logic, so I can use two flip-flops A and B to encode these two states, input and then the next state. And I implement this with two flip-flops, and then a couple of logical gates, and then that's it. So what is interesting here is you may say, okay, so what are these, two dashes there? So over there are two dashes. Those are the don't care conditions, which means that, for example, at state 0, 1, you don't really care what is your next state if your input is 0. So that happens in real life. But however, when we do design, you cannot say, okay, so current state A is 0, B is 1. If I give input X, my next state is unknown. Once you have this piece of hardware, it must give you a deterministic next state. So if we do a circuit analysis, we realize in those cases, both cases become 0, 0. And another thing which is a little bit hidden or tricky here is, because I'm having two flip-flops, so I have another case when both are 1. You don't really need it in your design, but when I finish the design, this system which has two flip-flops, it has the fourth state. No matter you like it or not, it is there in your system. And I need to do a circuit analysis trying to figure out the behavior of these two states as well. So now once I finish all these things, I try to build this state machine here. So now this becomes a complete state machine. It has 4 states, it has more edges. And all these new edges will be in red. And what happens now is it becomes the interesting question is, so that triangle is what I want. And then what you design for me is this guy here. If I do a traditional testing or verification, I'm only going to verify those black edges, the ones I want. And I see they are all here. You didn't do anything wrong. But I don't know anything about these red edges. And that is, I'm not interested in that, so I don't really care. But now if you think about from trust, from security, from access control. So for example, in the original system, nobody can access state 0, 0 because there's no edges going into 0, 0. But in this system, which somebody implemented for me, you see every state goes back to 0, 0. And nobody did this intentionally. It's just the system, the design tool does that. Because you said it is don't care, so this is do whatever things trying to optimize for performance. And performance doesn't include security and trust. Okay? So now this becomes something which I can skip quickly. So I can do a random walk trying to really figure out what is this thing we call the backdoors. So you design the system, you have some backdoors so people can go to some place which they're not supposed to go. And also there's something really bad, so people can add this thing called hardware Trojan to your system. Because they know you want to protect state 0, 0. And then instead of implementing this, they intentionally put these things back to 0, 0. So now they don't even have to do a random walk to explore what is the vulnerability. Because they are the system designers. They know the vulnerabilities. So they design with these backdoors. And they don't have to put so many edges going back to 0, 0, because for them to break into your house, they only need one access. So they can just put 1, which means that if they do only this one teeny change, it doesn't change the performance of the final design. Okay? So now let's come back to say, okay, you may say, okay, you are talking about these cases, which is in my real life, it is don't care, which means I may not have this input at all. Then should I still worry about this? So that is something this equipment shows you what people can do. These are the equipment that people do fault injections. They can change the value of your input. So for example, you say, okay, at that state, I'm expecting always 0, not 1. And then they can use this fault injection to inject a 1. And then that your system goes to that stage. And then do something bad. Okay, and finally we talk about, okay, so you have all these systems, or eventually the computer chips. So who built these chips for you? you don't build it by yourself, and very few people build it by themselves, or they're even big companies, they don't build it by themselves. They use foundries from overseas. So this is a picture, DARPA did it more than 2003 or 2006. So I think the figure comes from 2004, and then the BAA came in 2006. So that is the first of their 3 BAAs on trust hardware. This one is called the trust IC. And this basically shows you the supply chain. You start from this green one, which is the system specification. And then you go to the design, fab, interface, so you can fabricate these things. You build the mask, you do the fabrication, and then eventually you got the wafer back, and then you do the testing, you do the packaging, and then you deploy the system into field, and then you can monitor its lifetime. So only the first stage and the last stage, they mark in green, which means you can trust, because you have the control. And everything in the middle, you have no idea who is doing this. Even for the design phase, you say, okay, so design, I'm using this, for example, IBM to do it for me. They are signing all this agreement with me, so they are not going to give it to somebody else. But IBM cannot do everything by themselves. They have to use, tools. For example, the Synopsys tools, Cadence tools, or some other tools. And when they write software, that's the same. They have to probably use some other people's software package. So they got things from outside that may not be trusted. So this introduced a lot of problems for hardware design itself. And then at least some of them, people call it reverse engineer attack. And then overbuilding. So if you are building a chip, for example, Apple says, okay, I give this foundry to build, 10 million chips for iPhone, let's see, 8.0, iPhone 8. And then this foundry says, oh, you are going to build iPhone 8. So instead of 10 million, let me try to fabricate 12 million. And then with these 2 extra millions, I can probably sell it by myself. So that is called overbuilding. And also there's something called counterfeiting. So counterfeiting, in old times, people talk about they have an old processor, and then they try to remove the marker, and then try to mark it as a newer processor, which the system becomes bad. But nowadays, there's another direction of counterfeiting. So people are trying to counterfeit old products. And you feel this is probably strange. Why people trying to fake old products? So think about the collection market. You try to fake old, the stamps or coins. And this is the same thing. So if you have a couple $1 million of fighter jet, if one of the little device got broken, and you need to find this little piece, and you will not find it anymore because the manufacturers, they're not manufacturing it anymore. And you have to go to these people called gray market, trying to pay whatever the cost to buy that one. And then people realize the profit, so they are trying to counterfeit the old things. Okay, so they use new things, trying to assume it is the old one. And you say new things is better, but sometimes new things is not compatible with the old system. That will create problems for you. And hardware children, this is something I mentioned earlier, trying to embed something in the hardware, so to do something maliciously. And the information leaking, which is, for example, if I have an encryption module in my chip, and then somebody can put a small antenna next to the encryption module, and then before I encrypt the message, the antenna is going to broadcast this, or send it to some other receivers. So that is information leaking. They can all get this done by hardware. And the IP misuse, so I give one license of this software or this hardware, and I make this multiple copies. That is misuse. Or I try to resell it to somebody else. Okay. So a lot of these problems here. So now let's come back to this figure I used before. So we have the safe there. And then what you see here is you learn about things at networking level, talk about things at software, talk about things about crypto algorithms. And then eventually you need the safe, you need the hardware to do it. And I just told you so many vulnerabilities, so many holes in the hardware. And then you'll say, okay, so I have these things which I don't do the design carefully, so the key is there. I have these back doors, so the safe looks good from the front, but at the back there are a couple of holes which people can get in and then trying to steal my gold or my whatever valuables. So you say, okay, so this eventually tells us, in some sense, hardware become a weakest link. And the most recently, for example, the new AES standards, all the reported broken cases becomes from hardware side, not software, from hardware implementation, not from the crypto. Okay. So what I'm going to do in the next 20 minutes is going to talk about, from hardware designer point of view, how can we turn this weakest link to something which we call the great promise. What hardware can do for you, for security, for trust. In addition, trying to make your systems secure and trust, make it better. So I probably will talk about the TPM and the PAF, which is physical unclonable function, which is very, very popular in the past 10 years. And the hardware software co-design, this is something probably I'm not going to touch at all. Okay? And instead, I'm going to talk about something on IoT applications. Okay, so this is the old slides, and the supply chain gets zoomed out a little bit, becomes smaller. And these are the attacks or these vulnerabilities I showed you earlier. So the reason I'm showing this one first is, you talk about how to use hardware to make your system better. The first thing you have to do is you have to make sure your hardware is protected, is trusted. And if you are building hardware, you want to make sure you protect your intellectual property. You protect your system. So that is the first thing you have to solve is you solve the security problems for yourself. And then once you are done with this, and then let's come and talk about how I can use this hardware to implement crypto, to implement software security. And I'm trying to do even something better. Okay? So I'm going to give you a lot of terms, and I'm not going to go into any details here because all these things are pure hardware design stuff. So the first one is called the design obfuscation. We talk about this reverse engineering. People can peel your chip layer by layer, trying to figure out these logical gates, how they are connected, which logical gate it is. It is an AND gate, NAND gate, or NOR gate, and then eventually figure out the functionality of your system. So what design obfuscation does is trying to obfuscate these devices, the small pieces, small logical gates, or small design components, to make reverse engineering much, much harder. Okay? And another thing is called the digital watermark. So what you do in digital watermark is you try to embed some design constraints into your design. So eventually your design have a certain property. And eventually you can verify this property and then trying to say, oh, this is my design. So if somebody illegally copy your design, so they buy your design, which is people they can always do, they do it maybe from their competitors, trying to learn what their competitors is doing. Okay, so they do reverse engineering, and then they learn that. So if I put my watermarks there, they can still learn it, but if they do not learn all the details, they just learn the layout of my chip, and then they just refabricate it, and then I can cache them, because in the layout, I have my signature there, I have my watermark. And there's another concept called the digital fingerprint. So digital fingerprint is in some sense trying to identify every chip, every single copy of the chip. So this is important because if I sell chip to company A, I also sell chip to company B. And now I realize company C is also using my chip. So I'm going to say, okay, so company C, where did you get this one? So either A gave it to you or B gave it to you. So I want to make sure I can catch who does this. And I don't want to, blame the honest users. But if I give everybody identical copies, I have no idea who gave that. So that is the motivation to do digital fingerprint, trying to make every single system or every single chip, in some sense, different. And then eventually this digital fingerprint becomes more useful because this is, in some sense, like a vehicle or like what we call later hardware security primitives. It makes every single chip unique. Then eventually you can use this trying to do authentication of the device. And then you can see, okay, so we have this, all these Cisco routers. So if it has a digital fingerprint, and then eventually I can verify whether this package really comes from that router or not. Okay. And this is one thing, it's called IC, or integrated circuits metering. And it is designed for counterfeiting and overbuilding. So I'm going to meter, you have your meter for the electricity, for your water usage. So the user, in this case, is going to meter how many copies the manufacturer is going to fabricate. And then if they see something strange, if they see the manufacturer manufactures more than what I have asked, then I know this foundry cannot be trusted. Okay. And using this, they can also give some post-silicon control of the chip. So for example, I can say, oh, I'm going to ask you to fabricate 10 million copies. And then for each of these copy, And then I'm going to have a enable code. Once every copy is going to sell to the customers, they have a mechanism so I can remotely enable that one. For all those, illegally sold copies, then they cannot be enabled. So in some sense, it becomes useless. And finally, there are a lot of design verification tools. One of the things is called concurrent checking. So this one can be used to use redundancy built in the chip to check errors or design the difference. And this can be used, for example, to detect hardware trojans. Okay. So we have a lot of things people developed in the past 10 years or so trying to mitigate these risks for hardware design. So with certain confidence, we can see now the hardware design itself could be much more trustworthy. It is not something all the design tools that are just built to improve performance. Now we can consider trust. We can consider security. Now with this in mind, we can talk about once this hardware piece is trusted, how can we build trusted system on top of this? And the first thing I'm going to talk is this thing called the Trusted Platform Module. So TPM is a set of standards industry people, they put for the secure and crypto call processors or accelerators. And it is organized by an organization called the TCG, the Trusted Computing Group. And they work very close to us. So across the creek in that, the chocolate color building. So it is the incubator. So the Fujitsu lab used to work there, and they're the headquarters of TCG. Okay. And nowadays, when you talk about TPM, more people realize TPM as the hardware implementation or chip implementation of these specifications, these standards. And what is interesting here is, so you can people talk about the TPMs from Intel, from Toshiba, from everywhere. So eventually, most of these big companies, they try to build their own TPM chips. Okay? And these chips, they can be installed on the motherboard, so it can do a lot of useful things. And most importantly, they are going to do most of the security-oriented or related calculations and store secret keys, generate keys. And it doesn't do anything for networking security, so it is suggested it's better to be used together with firewalls, antivirus software package, and all these other things, or even biometric verifications. Okay? So it has its limitation, it has scope of work. So what are the main functionalities here? So I put a couple of things here. So first, they can do hardware authentication to verify this is indeed the hardware, the laptop, the cell phone, which it claims it is. And then they can do a runtime remote attestation, trying to verify the runtime status of the system. They can generate crypto keys, and then they can protect the keys. They can store it there. It's not going to store in the cache memory or main memory. And they can use this, implement hardware pseudo-random number generators on the TPM. So you don't have to use a software to do that, which is not secure. And then they can seal the storage, so you can put your password and encrypted keys, and then your digital certificate, everything into the TPM. So I don't have the slides for this, but in some sense, there are also a couple of questions about TPM. So first, the last bullet. You can store all these things in TPM, but once your TPM is compromised, all your secret is gone. And the second thing here is, if you come back here, we mentioned TPM is this set of specifications, which is assumed to be the same specification. And then why you see there's so many companies, they are building their own TPMs, building their own chips. So which means in some sense, they are not trusting each other. So that is the thing. So people build hardware, they are building trusted hardware, but they don't trust each other. It's like the same thing when you write softwares. People talk about the Java. You have a lot of Java package you can use. But when you try to borrow some of this, you have no idea why they designed that package. You use it, take your own risk. It's the same thing here. If Toshiba doesn't build their own TPM, they try to use Intel's TPM, and then take your risk. You never know what Intel is going to do on their TPM. Okay. So now let's move on to this something called hardware security primitives. And what we do here is, so this is the definition of what is a crypto primitives. So it is a low-level algorithm that can be used to build the crypto protocols for computer security or for secure systems. An example can be this as like one-way hash function, encryption, and public key infrastructures. So these things by itself, they may not be that useful, but once you put into any specific applications, they become useful, like a building block. For hardwares, we can use hardware. Once it becomes trusted, we can use these things to build the root of trust and then try to build on top of this building blocks, which we call the hardware security primitives. And this one can be something very, very interesting because it is not just a better, a faster, or energy efficient implementation of security protocol anymore. We can use hardware fabric. We can use their physical features to do something without crypto. So that becomes something very interesting here. So there will be some examples here, and I'm going to talk about some of this. Okay. So the first one is the things people call the physical unclonable function. And this is based on something called the manufacturer variation. So when you fabricate chips, there are a lot of concerns, a lot of issues you can never control. Like when you do the doping, when you put these chemicals on top of the wafer, you can never make them, exactly even. So somewhere will be thicker, somewhere will be thinner. Okay, and then because of that, the things, all these things, when you build them, like these inverters here, their delay or the speed will be, there will be a tiny difference. So the idea behind this ring oscillator path is, I build two identical ring oscillators, which is a sequence of inverters, and then you have a feedback. So I try to build these two identical things. If the design is perfect, then these two ring oscillators, they should have the same delay. But because of the manufacturer variation, they have a tiny difference. So I'm going to use this tiny difference trying to generate secret keys. So for example, on one chip, the first one make 79 rounds in the same time. And then the second ring oscillator make 96 rounds, which means the second ring oscillator is faster. So if this is the case, I can define, for example, this is a 0. And then for exactly the same structure, maybe on another chip, because of the fabrication variation, the top one becomes faster. Okay? And in that case, I can define this is a bit 1. And now you would ask me why this is safe. I'll call this bit is safe because if people, they do reverse engineering, they take a peel apart my chip, they are going to observe these two ring oscillators. But they have no idea it is a bit 1 or a bit 0 behind this. Because they have to put power on and let these two ring oscillators race to see who is faster, who is slower, and then decide what is the bit. And for most of the systems, whenever you put power on, there are a lot of starting from operating systems, trying to protect the system. We talk about the memory is not safe, because if the memory is volatile, what happens in those memories is people can, when the chip is power off, when you don't have any of these security mechanisms, people can go there and then try to get your key. In this one, your key is not there. The system has to be running. And there's another version called this path, it's called the arbiter path. So this one, this light green stuff is the one called the multiplexers. So it has two inputs, one and 0, and they have an input on the top, which is we call the selection bit. So based on this selection bit, you are going to select either 1 or 0 and then put that as the output. So it is like a choice. You choose one out of these two. And what I did here is I'm building a network of arbiters, multiplexers. So at each level, I make all these routings, all these wires to be identical, trying to minimize the delay caused by wire lengths. So eventually, you think about these multiplexers. So inside there, they have manufacturer variations, so their speed becomes different. So if I put the same selection bit on top, 0, 0, 1, and then if I apply this, give a signal from the beginning, and then for these two array of ring oscillators, so when the signal goes from low to high, and then the signal will propagate, you'll see two paths. Okay? So in this case, the top path becomes fast, it arrives earlier, so that is the D flip-flop. So the data comes in first, so this becomes a 1. And for the same design, another chip may have just completed the opposite one. So the top or the bottom one comes first. And that one is connected to this, the clock signal or clear signal. So now this one becomes a 0. So this flip-flop now is going to store either a 1 or 0. And that is for the same challenge or the same selection bit. Okay. So this actually gives you a lot of things. So now you think about, I can generate 1 bit without doing any random number generations. I use only hardware here. So there are a lot of security applications for PAF. So I'm going to list some of this and then not going into any details here. Okay. So I don't know what happened with BV at the end. So the first one is I can use PAF to do a secure key generation and the storage. And now also we can do the secret share. So people can share and then they can exchange during this challenge response. And then I can do a symmetric encryption. I can do random number generation. I can also do software binding or licensing. And these are all the applications. And for the second the second PAF I talk about, that one you have a challenge response pair. So I put a challenge here, and then you are going to respond a bit 1 or 0. So if I put a line, for example, 128 of these things here, and then you have simultaneously 128-bit response. Or if you say, I don't want that many, and then if I just give different challenges to this structure, and then I can generate multiple bits as your response. So then I have challenge response, and then with this I can do some other things, to do user authentications, to do device authentications, and then to do digital signing or digital signatures. Okay? So that is one application. And another thing we talk about the hardware which can help people to do is, this is a new project we just started. It is called a Memristor. And if you came to the IAI Colloquium 2 weeks ago, so there is this distinguished fellow from UC Santa Barbara give us a talk about Memristors. So he's the vice chancellor of UC Santa Barbara, and they talk about Memristor. So this is the very, very similar thing. But yeah, so this is was not invented. It is predicted by Leon Chuang in 1971. So what happens there is, this is something very interesting. So you see this diagram here. So I have the basic elements of the circuit. So I have the voltage, I have the current, I have the flux, I have and all these things there. And what you see here is they have some relationships here. For example, from voltage and the current, you can define resistor, and then you can design capacitor. You can design inductor on the other end from the flux and the current. So what Chuang realizes there's an edge missing at the bottom. So you see everything is connected except this Q and the phi there. Okay. So then he decided, okay, so if such thing exists, and then he assumed it exists, and then he called this one Memristor, and then he predicted some properties about this physical entity there. So there are some equations which I'm not going to talk about. And then they continue working on this, and then they come up with some other nice features. And all these properties, they are just, building on their imaginations. They don't have real physical things to implement this. So that happens in the late 70s. And then after that, it's just stay there. And people realize, they have some very, very nice features about this. So one of the nice features here is, so they have this thing called a no energy discharge. So the key thing here is this Memristor, it has 2 states. So to make it simple, one is called a low resistance level, the other one is called a high resistance level. So if the system remains at low resistance level, once you cut the power off, and then later on once you put the power on, it still remains at the same level. Which means if you use this as memory, and then your system is not going to leak a lot of power. So it becomes very, very promising. So people start, still working on this. But eventually in 2008, 2009, an HP lab, they published this work on Nature magazine. And they fabricate the first Memristor in their lab. And eventually what happens there is most of these things, when they observe from their experiments, just, in some sense verifies what Leon Tran predicted almost 40 years ago. Okay? So eventually there are just some of these informations here. And what is interesting for this talk here is, so as soon as people talk about the memristors in production or in real lab, they started study memristors for security. And there are about 1,000 papers talking about how to use memristors to build physical and global functions, to generate secret keys. And then they talk about how to use memristors to build secure memories, so attackers cannot go to those memories. And then they use memristors to build chaotic circuits. And then use this chaotic behavior trying to hide some information. And then they use this to generate true random number generations. And then they try to build crypto modules using this. And the one thing we are working on is we are trying to use memristor to build authentications, which I'm going to go very, very quickly with 2 minutes to tell you what's going on there. Okay? So the key concept here is we are going to apply charge or discard charge or power or voltage or high voltage or low voltage, we can consider as positive voltage or negative voltage to the memristors, trying to push it into the low resistance level or high resistance level. And instead of using a high voltage, which people do in real life for memory because they want to have a high speed. So because we want to do authentication, so we try to have a very small voltage. So that will take you time to charge or discharge your memristor. And then because of this time, and then we can build some information. So basically, during registration time, each user is going to register a random sequence. And then eventually when they do verification, and then this random sequence is going to be remembered in the memristor. And then when the user comes to the device, and then they put in their random sequence. If that sequence matches what is stored in the memristor, and then you'll see some behavior. If it doesn't match, you're going to see some other behavior. Okay? So that is, you see those things, you see the color probably will change. So that is when people decided to use these things, see the little colors, they change. So once I apply this voltage, those little things changes. So if it matches what I'm stored, that means I have authenticated this user. And this is exactly what you do for password authentication. That pause string on top is your password. And eventually this thing is going to be see whether it is verified or not based on the ending status of each memristor. If it matches what I have stored previously, then it's a correct password. And the interesting thing here behind all this thing is, when I do all this, I'm not doing any calculation. And why that is good? Because once you started doing calculation, we talk about this side channel things. So these are just the physical things. I don't do anything behind, doing any calculations.
You're saying that the state cannot be read out from the memory state.
So that is another thing I didn't talk in details. So you could read this, but the thing is for you to read memristors, you have to put voltage. And as soon as you put voltage to read this, it changes. Yeah. So that is the reason. Yeah. So that is the nice thing about this. Okay. So starting from here, I'm going to talk about some of this commercial stuff. So why IoT is important. So this one talks about the power grid. So we have all these new energies, and then the new power grid with these solid lines. So previously, this dotted line, so the power generation goes to transmission, goes to distribution, and then goes to customers. It is one direction. And now the smart grid, you have more players, and then it becomes bi-direction. They have a communication there. And then at the bottom of this power grid, there are, for example, in this case, I talk about the consumers. I have this smart home, I have the smart industry, I have the smart building. And in all these things, there are, for example, meters. And there are examples like all these applications, like your air conditions, your laptops, your lighting systems. Okay, and all these things behind them, they have hardwares. They have little controllers to control them. And we talk about the smart vehicles, cyber vehicles, all these things. They can do this communication between vehicles. This is called V2V. And then they can do vehicle to roadside infrastructure, V2I communications. And then inside the car, they have this, the entertainment system, what they call now becomes infotainment, information and entertainment. And then they have a lot of other things called, this thing is the remote immobilizer, which is encrypted in most of the cars. So when your car is stolen, if you report to the police, police can remotely enable this, so that car becomes immobilized, so it cannot be driven anymore. So there are a lot of sensors on the car as well, like the tire temperature sensors, air pressure sensors. So for all these things, at the end, there are little hardwares behind this. Okay, and finally, example is this one called medical devices. So I drew this cartoon here. So eventually, you have the doctor, you have the patient in the middle, and then they have all these communication things. And we are talking about pacemakers, insulin pumps, and a lot of things users or patients carry with them. And now what happens is, for these people called wearable or implantable medical devices, they have a lot of design constraints. People want it to be safe because inside your body. They want it to keep your privacy because now this thing is with you 24/7. And they want it to be secure. All the data, they collect your data about your health condition. You want to make sure it goes to the doctor, not to go to anybody else. You want it to be power efficient. You want it to be convenient, not like this guy carries something all the time. Okay? So then we talk about these things. So design needs here, these are the traditional design needs for hardware engineers. So we need the functionality, we need to design the size to be small, we need to have high performance, low cost, low power, high reliability, and then safeties. So after these 50, 60 years of hardware design, we have design tools which people call EDA tools, electronic design automation tools. They can take care of all these concerns. Okay? And for the IoT devices, when we design these things for Internet of Things, they have new requirements. So I put some things here. They want security, they want privacy, they want trust, they want ultra low power. And almost all of these things, they were not considered for the EDA tools when those tools were developed. So let you know I put a lot of this cross mark there. Okay? So then what happens there is, for all these systems, if you build software solutions on top of this hardware, that is not a true solution. It is not efficient. Because eventually you still have this hardware leaking the information. That is something I mentioned earlier. All these side channel attacks, all those things. Your software is safe, your network is safe, but this hardware at the end, by nature, they are not safe.
I have a question. In the context of IoT, what is the difference or boundary between security and trust?
So security here, normally we talk about, for example, you do encryption, your data security. Your trust, you talk about, for example, I'm talking with you, can I trust this device? So it's, in some sense, trust is more about authentication, identify right user, right people, and also it's talk about privacy. Privacy is closely connected with trust, because you don't want to give your private data into untrusted parties. Yeah. So it's different from security is more, in this context, it's more general, talking about you don't want people to see anything. It is encrypted. Yeah. So, but however, hardware itself has some properties which actually can make these things better than you implement at software or network level. Okay. And I'm just going to give you these items here, and I'm going to stop. So this, for example, with these things, we talk about these requirements: safety, privacy, security, power, and the convenience. So from hardware, pure hardware, I'm not talking about anything about the software. So we can make device authentication by using only hardwares. We can do some lightweight encryptions without using any encryption algorithms. So those can make your secure data communication secure. We can do some path-based attestations or authentications, trying to provide some of these things using hardware. Okay. And finally, this is a roadmap which is summarized some of our work starting from 1997-98 when I started doing my dissertation about these things. A couple of items we have been working on in our group. I'm not going to read any of this. So the key thing here is we try to focus on theory and practice, which in some sense becomes research and education. Okay? And we have been doing pretty well on this because research and education, they are in some sense hand in hand. And one thing we are lacking here is trying to make more impact to industry. Okay? And to conclude here, I'm using this famous quote, nobody's island here. So I'm saying as long as we have money, no matter if it's physical bill, dollar bill, $100 bill, or you talk about the Bitcoin, as long as these things exist, there will be security problems. There will be crimes. Even I decide to remove crime from the title of the slide. So crime will be there. So once there is crime, you have to think about ways to protect yourself. And another thing I hope you have learned here is hardware, people didn't think about that before, but once you make your crypto algorithm secure, once you make your software implementation secure, the attackers, they are going to attack other places. So this hardware becomes another attacking surface. And it is always the case that the attacking surface grows faster than the countermeasures. So when we started implementing the cryptos in hardware, then this introduced hardware as an attacking surface. People started attacking your hardware. And I mentioned this here, no system is an island either. You cannot separate software, crypto, hardware, network, communication, and user. All these things, they have to be together to make a whole system. That is something we call this a holistic approach. If you want to have a secure system, every single item, every single link has to be secure. Okay? And people always say that the user, which I put in capital, that is the weakest link. So how many of you use passwords which is related to your personal information? How many of you use password for different sites? The same password at different places. So it happens. So that is the key thing here. And hardware is not just an enabler. It is also, it's not only an enhancer anymore. It can make your system faster and also can do something much better than doing something that software network cannot do. Okay? And finally, we come back to this safe here. So that is the start and then also the end. So I copied some cartoon here. So we're trying to build this safe. So we start from here, trying to fine-tune all these things here. We talk about these vulnerabilities. So we do these things and make all these changes, eventually build a fantastic safe. And then you realize what happens here is this is a paper safe. Which means if you design your crypto, which is you try to turn this, keys or these locks, you develop your software. And then eventually you build all these things on something untrusted hardware or on some hardware which has a lot of backdoors. That is something you build a safe of paper. Nobody cares. They can just smash it and then get whatever you stored inside. And that is the end of my talk. Thank you.